Okay, so this is joint work with my brilliant former student, Shaowei. I'm going to start this talk by taking the position that we should be able to understand how changing a program is going to affect our analyses. So this is important to software developers who are constantly changing their code and need to understand, for instance, how a change is going to impact a list of warnings that they get from a static analyzer. It's also important for program analysis designers because we incorporate transformations in our tools, and we want to understand whether a transformation is going to make an analysis better or worse. But many analyses fail to meet reasonable expectations in these regards. So let's take as an example this program. Suppose that we analyze this program using showing a polyhedral analysis, and we find that I must lie in the interval between 1 and 5. And then we insert an extra variable j that accumulates the sum of all the values that I takes, and then we analyze it again using polyhedral analysis. So our expectation is, because I haven't changed the computation of I at all, I should still be able to prove the same interval that I had before. But as observed by Magnot and Leguin, in fact, just by inserting this j variable, I can no longer prove the lower bound on I. Another example, let's take this little nested for loop, and we're going to analyze it with, say, ultimate atomizer and prove that it terminates. And then we're going to replace this symbolic constant n with a concrete constant, 4096. We'll analyze it again, and our expectation is that, of course, we should be able to prove termination of the program on the right, because to prove termination of the program on the left, we must have proved termination for all values of n. Certainly, we can prove it for 4096, but unfortunately, ultimate atomizer is going to time out after 15 minutes. So these are perhaps toy examples, but it's a real phenomenon. So for instance, in this experience report on the commercial static analyzer covariety, there's a whole section about the frustrations users have with unstable error reports and the lengths that they go through to avoid them. So they disallow certain analysis techniques that lead to more unstable reports. There's also a slew of other reports of unstable behavior and counterintuitive results in program verification and static analysis, which is nicely summarized by this quote by Leno and Moskal, that tools can understand our programs, but we cannot understand our tools. All right, so this work takes a step towards fixing this problem. So I'm going to answer two questions in this talk. First, what is robustness? So I'm going to give a general language for talking about robustness properties and criteria by which we can understand programs satisfying these properties. And then in the second part, I'll talk about how we can achieve robustness, how we can design analyses that are robust with respect to these criteria. So the overall goal is to provide qualitative guarantees about how we can expect program analyses to react when we change an input program. All right. So informally, we say that a program analysis is robust if it preserves relationships between programs. So this isn't really just one thing. It's a class of properties, because there's lots of different relationships or transformations we want to be able to understand. There's a great number of different robustness properties we might be interested in. So it's really a family of correctness criteria that is indexed by the class of relationships we want to preserve. And our goal is to develop sort of an abstract theory of robustness that doesn't commit to a particular class of relationships or a type of analysis, but allows us to talk about robustness in a more abstract setting. So you can think of this as trying to do for robustness what the theory of abstract interpretation does for soundness. So just a general mathematical language for talking about these things in the abstract. I'm going to start by using a concrete example. So intuitively, program analyses shouldn't depend on the names of variables. So let's suppose that we have an analysis A that maps programs to transition formulas that over-approximate their dynamics. So this is just a logical formula over unprimed and primed variables that represent the state of a program before and after an execution. And the robustness property that we're after is that if P and Q are two programs that are equivalent modulo some renaming of variables sigma, then the same should be true for the two transition formulas assigned to P and Q by the analysis A. All right, so let's graduate from sets to categories. So we're going to define a category of programs wherein the objects are programs, and the arrows are exactly these equivalence modulo renaming relationships. And we'll define a similar kind of structure for transition formulas. Objects or transition formulas, arrows are entailments modulo this renaming, taking care to rename prime variables appropriately. So the idea that A should be invariant under renaming of variables should imply that we can lift A from a set that maps programs to transition formulas to a functor that maps this category of programs to the category of transition formulas. So every arrow between two programs P and Q should correspond to an arrow between the transition formulas A of P and A of Q. But this isn't quite what we want. Not only do we have this correspondence between arrows, in some sense they're the same arrow, right? They should correspond to exactly the same substitution. So to encode this, we're going to add another category, a category of finite sets and bijections. And we're going to equip programs and transition formulas with faithful functors into this category. So intuitively, for each of these arrows, we're going to forget about programs and transition formulas and project onto just the underlying substitution. And then the statement that A is invariant under renaming is exactly the statement that this diagram commutes. So for every arrow between two programs, there's a corresponding arrow between transition formulas. And moreover, they correspond to exactly the same variable renaming. All right. So now we can talk about this language of robustness. The basic structure of interest is a concrete category, which is a category C equipped with a faithful functor into a base category B, which we think of as the class of relationships or transformations of interest. And then the fundamental map of interest is a concrete functor. So a concrete functor between two concrete categories is a functor between two concrete categories over the same base that commutes with projection. So every C arrow has a corresponding R arrow that both project onto the same B arrow. And now we can take this very abstract view that a robust analysis is just a concrete functor. So it's an analysis that preserves transformations, but we're using this highly abstract mathematical language. We already have a nice abstract mathematical language for talking about program analysis. It's order theory. It's the theory of abstract interpretation. So let's compare with that. So we don't lose the ordinary order theoretic vocabulary of abstract interpretation when we move to concrete categories. Every concrete category can be equipped with an order relation, which is defined by the set of arrows that project onto identity functions. So this always defines an order, and it allows us to recover the usual approximation order that we expect in abstract interpretation. So in the paper, we redevelop some of the theory of abstract interpretation in this more general language of concrete categories. So we can still do a lot of the things we expect to do in abstract interpretation. The thing that we gain is the ability to talk about approximation modulo transformations. So if we think of our base category B as a set of transformations of interest, then arrows in our concrete category correspond to approximation modulo some transformation. So this could be a renaming of variables. It could be a linear transformation. It could be a control flow transformation, this sort of thing. All right. So the next question is, can we actually design robust analyses? So in fact, there are robust analyses, but we have to be careful what we mean by that. Robustness is not one thing, it's many things. And so this depends on the class of relationships we want to preserve. But something we notice with this sort of profile of robustness properties of various classic abstract interpretations is that there's a tension between precision and robustness. As we get to more powerful analyses capable of proving more things about programs, these analyses tend to be less robust. And the reason for this is that a lot of the basic building blocks of program analysis, like widening and Craig interpolation, guess and check loops using LLMs, these are all sort of sensitive to representations that make them have poor robustness properties. So if you want to build a robust program analysis, you sort of have to take all of these nice tools off the table. So there's a question of whether we can actually design analyses that are precise like these analyses, but also have better robustness properties. So over the last few years, my group has developed a number of techniques that have shown that it is possible to design monotone program analyses that are competitive with state-of-the-art abstract interpreters and software model checkers. And they all follow the same basic recipe. So we'll take some theory paper that shows that some property of a sub-Turing model of computation is computable. And we lift that to a program analysis using the pattern that we first take our loop, we abstract it in this sub-Turing model of computation, we analyze the model, and then we translate the results back into an over-approximate analysis of the input program. So these are all intuitively instances of the same recipe. In this paper, we show that they are actually formally instances of the same recipe. So there is a category theoretic explanation of all of these analyses, wherein we say, we imagine that we have a concrete functor that maps D to R, where we think of D as being a sub-Turing model of computation. Then we can lift that functor from D to some larger category C, provided C has best abstractions in D. So this is really like the technical meat of all these papers, is proving this like best abstraction result. But we have this, the takeaway here is that we have this like very general recipe for showing that if you have a sound and robust analysis that's just defined on D, we can always lift it to C. So the content of this is number one, we sort of don't need these bespoke correctness proofs for all of these papers anymore. They're just instances of this one general recipe. But maybe even more exciting is that the conclusion of this theorem is stronger. So not only do we prove that these analyses are monotone, this theorem shows that these analyses are robust with respect to linear transformations, which is a much stronger result. All right, the last thing I want to talk about is sort of the end-to-end story here. So all of these analyses that I had on the previous slide were loop analyses. They apply to a single loop. And the way that we apply these to real programs is using the framework of algebraic program analysis. So the setup is that we take our control flow graph, we compute a regular expression that recognizes a set of paths of interest, and then we interpret that expression as a transition formula that over-approximates all the paths that are recognized by that expression. And the way we do this is by reinterpreting all of the regular expression operations as corresponding operations on transition formulas. So the connection is that you can think of these robust loop analyses that I was talking about earlier as just different implementations of the star operator. So this raises the question of, in what sense is this entire pipeline robust? What kind of transformations can we do to whole programs, given that all of our operations are robust? What's the end-to-end story? So the bridge here is that this strategy that we have for lifting concrete functors also allows us to transport natural transformations. But the concrete payoff of this is that we have a general way of proving that these iteration operators satisfy certain algebraic laws. And then using these algebraic laws, along with the robustness properties of the individual operators of the analysis, we can show that algebraic program analysis is robust with respect to a class of loop-preserving stuttering simulations, which I don't have time to get into, but I will give you a couple of examples. So if we take a loop and we unroll it some number of iterations, or we split it into a couple of phases, these are transformations that are guaranteed to make my analysis more robust or more precise. All right, so summing up, I think predictability of program analyses is a really important and understudied topic.
Fire alarm. Yep. Sorry, Zach.
Really cool work. Fantastic talk. Thank you so much. I was curious about the relationship between incremental algebraic program analyses and robust algebraic program analyses. Could you just say more about that Venn diagram?
Yeah, so I think robustness is a nice property to have for incremental analyses as well. In that, I think Evan did some work on incremental analysis in a non-algebraic setting and encountered issues where if you restart an analysis versus doing it incrementally, you end up with different results and like how to overcome those kinds of problems. Robustness, I think, helps you a lot there because you can actually guarantee that you're going to, like, it's deterministic. Yeah. It's invariant under a bunch of nice transformations. So yeah, I think that there's a good case for why you want both incremental and robust analyses, but I don't think that they interact in the sense that incremental analyses make it easier to be robust, or robust analyses make it easier to be incremental. But I think it's important to have both those properties. And the algebraic framework allows you to do both, which is a nice property.
Hi, how's it? Great talk again. So you mentioned towards the end about preserving across different program transformations, you can increase your precision of analyses. And I'm wondering if sort of the compositional nature of that is if I go through a compiler pipeline, I do a bunch of different transforms, ideally maintaining equivalence through all of those. And at different phases, I can get different precision of some sort of static analysis. And I'm wondering is, as you go through and do this, should any results at one stage, just going from program A to B, apply all the way through the pipeline? Is this compositional, or is there like a gotcha if I chain a bunch of this sort of analysis together?
So the setup is that you transform, reanalyze, and the question is, what's the gotcha that you're worried about?
I'm hoping you can tell me.
So if you can prove that your analysis is robust with respect to the transformation that you're talking about, then maybe that's an indication that you don't need to rerun the analysis from scratch. Maybe you don't need to rerun the analysis at all. So maybe there's a performance story there. But if the transformations are, say, precision improving, you wouldn't want to do that. Maybe this is an argument for why you should wait until the very end to do your analysis rather than doing it at every step. Yeah, that's an interesting question.
Thank you.
Hi. Thanks. Very nice. I have a question about one of your diagrams. I guess the one where you first abstract to a sub-Turing model and then you analyze that. Uh-huh. And you said that that's always robust. I'm curious if it may be the case that the abstraction is not robust, and then you lose robustness because of the abstraction.
Yeah, so there's more to the story. You have to prove that this is actually a best abstraction. So you can't just take any old model. It has to be the best model in some sense. So the best model is it's kind of like a Galois connection. So this weak left adjoint is really saying not only is it an abstraction, it's an abstraction that satisfies a universal property. And it's that universal property plus robustness of the analysis on D that gives you robustness of the
Okay.
analysis.
Cool. And I guess a follow-up question. Have you thought about how that might change if you have some kind of abstraction refinement, like a Seeger loop going on?
I haven't thought about abstraction refinement. Abstraction refinement is one of those things that's really hard to make robust, particularly because we often do abstraction refinement by sort of guessing like a separator between our reachable states and our error states, and that guess is often dictated by a SMT solver, and if you have a different naming of variables, you're going to get different models or different unsat cores, and end up with a lack of robustness. So that's a good question how you could do refinement with this. Maybe another answer to this question is this best abstraction result is really saying that there's no way to refine this abstraction in some sense. At least if this is your set of abstractions, this is the best one you could possibly do. Mm-hmm. So like this is something that, for instance, predicate abstraction, it doesn't have, you don't have a best predicate abstraction unless you have a finite state program. So we're working with models where you can really get like best abstractions.
Okay, cool, thanks.
Cheers.
Let's thank the speaker again.